Hello everyone, Mr. Boltri here, bringing you video 1.5 of AP Physics C, in which we are going to be introducing the calculus concept of derivatives. So in order to do that, we are going to revisit the Marble Lab, define a derivative, talk about derivative notation, and then introduce what's called the power rule for derivative. So to get that started, let's remember back to the Marbles Lab where we had a marble rolling down an inclined ramp, and we got this curvy quadratic position versus time graph. So what we wanted to do with this position versus time graph is we wanted to make the velocity versus time graph. And we know that the slope of a position versus time graph is velocity. But this position versus time graph doesn't have a slope, it has a curve, which is made up of a bunch of different tangent slopes. And so what a tangent slope is we draw a tangent line at a particular curve and then find the slope of that tangent line. So what we had to do is we had to go through and draw a bunch of tangent lines. For example, here's the tangent line at time 2 seconds. And then if we find the slope of that tangent line, it tells us the instantaneous velocity at 2 seconds. So if we go through and we do that a bunch of times, what we end up getting is this velocity versus time graph, which is made up of a bunch of different instantaneous velocities, a bunch of different tangent lines, and then the slope of those tangent lines. So we can actually use Desmos to give us the equation of both of these graphs. Using the curve of best fit function, we can find that the position versus time graph has an equation of 4.35 t squared. So it actually does turn out to be quadratic. And then just using our classic old friend y equals mx plus b, we can find that the velocity versus time graph has a function of 8.7 t. So as time increases, the velocity increases at a constant rate. We've called that rate the acceleration. But we had to do so much work to get this velocity versus time graph. We had to draw a bunch of different tangent lines, find the slope of all those different tangent lines, just to tell us what is the function of the velocity with respect to time. If only there was an easy way to just get this position versus time function and turn it into a velocity versus time function in like one easy step. That would be really awesome, right? Well, hopefully you find derivatives to be awesome, because derivatives do exactly that. So first, let's define what is a derivative. So the derivative of some function, we'll say f of x, tells you the rate of change of the function of f of x. So to say that another way, f prime of x, which is just another way to write the derivative of the function f of x. So f prime of x is an expression. It's going to give you another function, which tells you the slope of the tangent lines to f of x for all values of x. So specifically, like for example, if you take the value of x and you plug it into the first derivative, f prime of 2, then that is going to tell you the slope of the tangent line to the function f of x at the value x equals 2. So that was a lot. For me, this isn't going to make sense until we talk about a specific example. So let's take the function f of x equals 12x minus 17. So I chose this example because it should be pretty easy, pretty straightforward, because it is linear. So if I wanted to know what is the slope of this function at x equals 1, all I do is rise over run, and I find that the slope is 12. What about the slope of the function at x equals 3? Also 12. So if I were to make a function that told me the slope at a whole bunch of different values, that function would be f prime of x, or the derivative of f of x, equals 12. Because no matter where I look at the slope of the function, the slope is always going to be equal to 12. And just to prove it, I could plug in f prime of 4 equals 12, which then going back over to the original function, the slope at 4 equals 12. So that's just kind of the very basics of what derivatives can do. So before we dive too deep further, let's just talk about a little bit of derivative notation. So like I've said, if we have this function f of x, we can write the derivative of the function f of x using a little dash. So this f dash of x, which we read f prime of x, that just means the derivative of the function f, and we get f of x. Another way that you could write that is this dx business, which you see also here, which this is just the derivative of y with respect to x. Down here, this is just the derivative with respect to x of the function g of x. So these are just three different ways that you might see derivative notation. But this is probably stuff that you're going to see more in math class, where we're dealing more with f of x, g of x, and y equals. In this class, we're going to be using stuff more like position, velocity, and acceleration. So we would call this x prime of t. And instead of our functions being in relation to x, oftentimes they're in relation to something like t. So you might see something like x prime of t, which is just the derivative of the position function with respect to time, dv dt, which is the derivative of the velocity function with respect to time, or d dt of the at function, which is just the derivative of the acceleration function with respect to time. So those are just some of the different ways that you might see derivative notation. And now, let me just sort of blow your mind a little bit further, is that you can actually take the derivative of a derivative too. So here we have our f of x, and then we have the derivative function of f of x, which f prime of x tells me the slope of the tangent lines to f of x. So f double prime of x, the second derivative, is going to tell me the slope of the tangent lines to the first derivative. So if we were to draw tangent lines here, we see that the slope, this function has a constant slope of 0 the whole time. So the second derivative is going to be pretty basic. It's going to just be 0 the whole time. And all that says is that if we were to choose any point, like let's say x equals 4.5, and what is the slope of the tangent line there? It's 0. Okay, and so f of f double prime, the second derivative of f, evaluated at 4.5 is going to equal 0. So this is a really basic example, but let's back up a little bit and see if we can notice any patterns from before. So how do derivatives tie in with physics? So we said earlier we had our position versus time graph, and we worked really hard to try to figure out what are all the values of the tangent slopes at a bunch of different times. So then we got this velocity versus time function. But let's just evaluate the velocity versus time function at 2. So that just tells me that the velocity of the object at 2 seconds is 17.4 meters per second. So if I try to translate that to the position versus time graph, what does that mean? Well, that means if I were to draw a tangent line at 2 seconds, the slope, the instantaneous velocity, the slope of the tangent line would be 17.4 meters per second. So then I think you would agree with me, hopefully, that it's fair to say that the velocity versus time function is just the derivative of the position versus time function. And likewise, we could then go and take the derivative of the velocity versus time function. So if I try to figure out what is the slope of all the tangent lines at in regard to the velocity versus time function, I would see that the slope of all the tangent lines is the slope, because it has a constant slope, so it's just 8.7, which we remember is the acceleration versus time. So then it's, I think, fair to say that the acceleration is the derivative of velocity. And since velocity is the derivative of position, we can then conclude that acceleration is the second derivative of position. So let me just show this to you a little bit more visually. So if we start with the position versus time graph, and then we look at all the tangent slopes, and we try to find a function that tells us the meaning of all the tangent slopes, that's called taking the derivative. And we know that the slope of a position versus time graph is velocity. So by taking the derivative of the position versus time graph, we get the velocity versus time function. Likewise, we know the slope of the velocity versus time function gives us the acceleration. So by taking the derivative of the velocity versus time function, we get the acceleration versus time function. But this is all hypothetical because I'm just saying take the derivative, and we don't yet know how to take the derivative. So what we're going to do now is we're going to try to recognize the pattern in how you can take the derivatives of a polynomial function, and that will allow us to actually perform this mathematical calculation. So here are the two examples that we have talked about so far in this video. And I want you to look at them and see if you notice any patterns with what happens when we move from the original function and what happens when we take the derivative of that function. What changes about the f prime of x or x prime of t? And then what happens when we take the derivative again? What changes now? So if you need just a little bit of help seeing the pattern, what happens if I add exponents to all of the different variables? Then do we notice what is changing about the different variables now? And if you were to have to write out what that pattern looks like, what would you say? Another way to say that is if you had to solve it, if you had to write the pattern with variables, what might that look like? So if we have just this random function x raised to the n, what would happen if we took the derivative of that x raised to the n? Well, so I hope a lot of you guys are seeing that what happens is the power gets multiplied to whatever constant is hanging out in the front, and then gets reduced by 1. Again, the power gets multiplied by the constant that's hanging out in the front, and then gets reduced by 1. And that's exactly what we end up with. We take the power, x to the n, multiply it by whatever's hanging out in the front, and then reduce that power by 1. And that is called the power rule for derivatives. So now I just want to take you through a quick example of how derivatives are so powerful. So let's say we have this crazy cubic position versus time graph. The object is just like flying all over the place. And we were asked the question, well, at what time or times does the object change direction? Well, we can look at the graph and say, well, it's moving in the negative direction here, and then it turns around and is moving in the positive direction. So kind of in this region, and then same thing, it's moving in the positive direction, turns around, and then is moving in the negative direction, so kind of in this region. But as far as AP concerned, kind of here and kind of there are not acceptable answers. We want to be very specific with our answers. So you might be able to use your calculator to try to triangulate, well, what is the exact coordinates of this? What is the exact coordinates of that? Or you could use our new powerful derivative rule. So if we try to think about, well, what does changing direction mean in terms of the velocity? Well, that means that the velocity is moving from either negative to positive or positive to negative. But in order to even start looking at that, we need to make the velocity versus time function. So we know that the velocity is the slope of the position versus time graph. So we are going to just take the derivative of the position versus time graph, and that's going to give us the velocity versus time graph. So I know this is brand new to many of you, but I want you to just go ahead and give it a try to see if you can get what the velocity versus time graph is using those power rules for derivatives. And by taking the exponent, multiplying it down in the front, we can get the velocity equals -9 t squared plus 10t plus 4. But then what do we do with that? We can graph it and see, okay, it looks like this. But what is our initial question? Okay, well, what time does the object change directions? Well, that's when the object goes from moving in the positive direction to moving in the negative direction. So just to look at this, we have a bunch of negative velocities, which means that if we translate that back to the position versus time graph, the object is moving in the negative direction. And then we have some positive velocities for a little bit, which means the object is moving in the positive direction. And then it goes back to having negative velocities, which corresponds to the tangent slope of the position versus time graph. So then if we figure out when the object goes from having a negative velocity to having a positive velocity, we can figure out when it turns around. And finding zeros in your calculator or just mathematically is a lot easier than trying to isolate this random point on a graph. So we can find the zeros and we can know that the object turns around at exactly this time and exactly that time. So that's going to be our answer to this problem. So this is, for many of us, a very new concept. And so you might have to give it some time to sink in, but we are going to be practicing derivatives all year, both in this course and in your calculus course, or multivariable calculus course too. So this is not, while this is a new concept now, it might not click right away. It's not going to be something that's going to go away. It's going to be something that we're continuing to practice. But if you have any questions just off the top of your head, please let me know, and we will do some practice problems with derivatives in our next class. This is Mr. Boltri wrapping up video 1.5, where we introduced calculus for the first time by talking about derivatives. Go Bears.